Hey, welcome back, everybody, to part two of Dr. Kevin Henke and Dr. Gary Loechelt on the creationist claim of helium diffusion rates. I know last time we had a lot to talk about on this particular topic, but unfortunately, we didn't break it down probably as simplistically as we should have. So before we even get into this, what we're going to do is we're going to take a little back step, and we're going to have Dr. Loechelt spend a few minutes just basically talking about the creationist claim itself. And if you're not familiar with this particular claim, you can actually find it on Talk Origins. It's creationist claim CD015. There's also many articles on there by both Dr. Loechelt and Dr. Henke. So if you want to read up on it, that's the perfect place to go. Some of the links are broken. However, the links that are working, I've included in the video description. So you can actually go right to their PDFs and right to what they've written and take it from there. So before we get into the technical stuff, because I've seen Dr. Loechelt's presentation and it's excellent, but it is technical, not going to front. There is a little bit of knowledge that needs to be, required to kind of get a full understanding of this. But I don't want, again, that to turn anybody off, because I know a lot of people don't have a huge background in physics and maths, and I get that. But this is something that I think that everybody should be aware of, because this is one of those claims that does come up every so often. And it's one of those claims that is very difficult to refute if you're not that familiar with it. So I think that if you get like a tertiary understanding of this particular claim, it's at least enough to say, okay, this is why Dr. Humphreys, who most of his claims are from, may have made some mistakes or may not be correct. And I have reached out to Dr. Humphreys. He wasn't available for a couple of days. He was out of town, but he has said that he'll review the first video we did last week on last Friday, January the 12th. And he will review this one. So hopefully once he gets a chance to look over the videos, he'll give us his side of these things, and I'll post it on the Great Debate Community webpage, because I want to be fair to all parties. So Dr. Loechelt, real quick, do you want to briefly give us an introduction to this particular claim, and then we can start the presentation so people that are not aware of it and are not very sciencey can kind of understand it?
Yes. Well, actually, I have something like that in my presentation. So should I just begin?
That'd be fine too. That'd be fine.
Yeah. So let me just start from the beginning. So thank you, everyone. My name is Gary Loechelt, and I have a PhD in the Science and Engineering of Materials from Arizona State University. And as Steve McRae said, today we're talking about helium, diffusion, zircon, accelerated nuclear decay, and the age of the Earth. So it's an interesting combination of topics. The focal point of this work was a set of geothermal test wells in New Mexico. The backdrop on the title slide, can everyone see the slides, by the way?
Yeah, I can see the slides.
Okay, yep, good. And you know what? I'm going to present you a little bit better. Just there we go. Okay.
So this is actually from the Valles Caldera in New Mexico. It's a picture I took, and you can see this all was one big volcanic caldera. And let me just say a little bit about myself, my background. My bachelor's degree is in physics from the University of Washington. I have a master's degree in applied physics from Cornell University. And my PhD is in the Science and Engineering of Materials from Arizona State University. And while I was an undergraduate, I worked for 5 consecutive summers at the Hanford Reservation in Eastern Washington. That is famous for being one of the original Manhattan Project sites. And at that time, I was really more on a nuclear physics career track. In graduate school, I shifted direction to solid state electronics, and that has been the field that I've been employed in for now 20 years or more. And over the course of my career, I've held various roles in technology development and discrete power devices. I've published a number of papers in academic journals and conferences. I'm an inventor on 54 US patents, and some of my technical skills and areas of expertise are in the area of physics and computer simulation, modeling, and programming. So that gives you an idea of at least my technical background. As far as personally, if you just want to know where I'm coming from on this topic, I am a Christian. I believe in the Bible. I don't accept the young earth claims, but I do believe in the Bible, in a creator, and in the Christian message. The RATE study actually was very interesting to me for several reasons, because it really it touched on multiple areas of my life. There's the religious component. It had an element of nuclear physics, which goes back to my undergraduate days. And in the semiconductor industry, I work with solid-state diffusion on a very routine basis. And I've probably run literally over the course of my career thousands, if not tens of thousands, of different diffusion simulations in the course of trying to model the manufacturing of electronic devices. So it is something I'm very familiar with, I'm very comfortable with, and since that is a large part of the RATE argument, it was something that really appealed to me technically. So let's put this whole debate into context. And the whole RATE argument was from a group of young Earth creationists. Now, their belief is inconsistent with the scientifically accepted age of the Earth and the universe. So right there, there is a, they question the scientific age. So in addition to the biblical argument, they want to look for scientific evidence. They want to look for phenomena that they believe is inconsistent with this position. Things that, if they can demonstrate there are certain things, phenomena that could not be sustained for a billion years, that would call into question the commonly accepted age of the Earth. So several decades ago, back in 1982, a young Earth creationist was working on some samples from geothermal test wells in Fenton Hill, New Mexico. In the course of the study, they were looking at the lead content of these crystals and also the helium content. And they noted that there was a surprisingly, or what they considered to be a surprisingly large amount of helium in these crystals. And the current temperatures down these wells was fairly substantial. So they thought, well, Gentry and his fellow young Earth creationists thought that it's unreasonable for helium, which would be a gas that could potentially diffuse rather quickly through materials at low temperatures. It seemed inconsistent that there'd be such large amounts of helium in these crystals. So subsequently, this was about almost 20 years later, there was a team of young Earth creationists who came together to start a research program. And it was called RATE, for radioisotopes and the age of the Earth. And it was actually a multi-pronged program with several different tracks, the helium diffusion being just one track of it. And they had different lead scientists for each track. But the overall, I guess, the purpose of the program was to try and reconcile a young Earth model view with radiometric dates, which typically show much older ages for rocks. And their underlying belief was if nuclear decay rates were accelerated at any time in the past, you could have large amount of decay products in a short period of time. So that was really, really underlying this whole program. Regarding the helium diffusion, the basic points were that they did not believe that helium could be retained by these crystals for billions of years. The problem, though, is if you believe in just 6,000 years, there wouldn't be any helium there in the first place. So already there's an inconsistency, you might say. So they had to invoke a second point, and that is you have to accelerate the nuclear decay to get the helium in the first place. And then because after that, the crystals have only been around for 6,000 years, there's not much time for the helium to leave. So that is their explanation for why there's these large amounts of helium in the samples. And to support this hypothesis, the RATE team selected Russell Humphreys, who has a physics background, to construct a diffusion model of the system. And they claimed that based upon their modeling, that there's convincing evidence for young Earth. Now today, on the debate, I will focus on the validity of this model. Last week, Dr. Henke addressed other aspects of the RATE claim. I mean, things regarding the validity of the data itself, questions regarding how they analyze the data and handling the data, which are valid criticisms of the RATE hypothesis. But I just want to focus on this one aspect, because even even if you assume there's some validity to the data, and I really do believe that there is a phenomenon that they observed that deserves an explanation, that the rate argument basically lives or dies based upon the validity of the model that they created. And let me just say a little bit about technical expertise, because it is a very mathematical subject, and for those who do not follow the math in detail, you're standing at a distance trying to judge who did the math right. Well, the best I can do is just present some of my credentials, and I'll give an example of something that I published in the academic literature. This was measuring and modeling of boron diffusion in silicon and strained silicon germanium epitaxial layers during rapid thermal annealing. And that was in the Journal of Applied Physics back in 1993. And my main point, I'm not going to talk about the equations, but it's just to say I am comfortable working with solid state diffusion. I've published in that field. It's something fairly well known. And this is an example of just something from Humphreys' side. And it's at a level that I would say, a technical level that I would consider typical of, let's say, an undergraduate textbook, not really what I would consider to be state-of-the-art kind of diffusion science. And just to give an example of equation 3, he had two different mechanisms for the diffusion, and he just simply added them together. And this in itself, it may seem to be a reasonable thing, but it's very, there's really not a good explanation for it. And let me just give you an example of this. And I'll use a highway analogy, but imagine that you have, with diffusion, we're talking about the transport of atoms and things through material. So imagine like a highway system across the state. Let's say you have a freeway that goes across the state. Let's say you have a highway next to it, a country road. Let's say on that highway, on the freeway, you can count the number of cars per unit length. That gives you a certain density. And you could stand at a state line and you can count the number of cars that cross that state line per unit of time. And then you could also calculate a velocity, an average velocity for the car, so many miles per hour. And if you know how many cars there are per mile, if you know how many miles per hour they're traveling, you take the product of the two, you would get how many cars would cross that line per unit time. And you could do the same for the parallel road, the country road. Now, let's say you have these two densities. If I want to know the total density of the highway system, I could just add those two densities and get the total density. If I wanted to know the rate of cars crossing the state line, I could just add the two rates and I get the total rate. But let's say I want to know the sort of a mean velocity. Let's say the freeway was going at 60 miles an hour, the other road at 30 miles an hour. If I told you, well, if I have one road going 60 miles an hour, one road going 30 miles an hour, then the total velocity must be 90 miles an hour for the system. That's adding the velocities, and that's something you wouldn't do in a transport problem. That is essentially what Humphreys is doing here. He's adding two diffusivities, but the diffusivity plays the same role in diffusion that velocity would in the traffic example. He's adding two quantities together that really should not be added. So I do want to direct some questions to Humphreys. And first, I would just like for him to explain where he got equation 3. I've not seen in my background. He did not present any references for it. He did not give any proof. So I would like to see how he got equation 3 and also why he didn't give a reference or some kind of proof behind it. So having said that, let's look at the actual data and the model and the specific claims. So these are the claims that Humphreys made regarding the helium diffusion. And let's look at the graph first, because the graph really captures a lot of things. What Humphreys tried to do was create a model for the helium diffusing from these zircons. And he created two models. One model was based upon young Earth premises and had a model time of 6,000 years. And the other one was an old Earth model. He calls it uniformitarian model. And it had a time factor of 1 billion years, over 1 billion years. And from these models and the amount of helium that Gentry had observed, he calculated an effective diffusivity. And then they also commissioned a researcher to measure the diffusivity. And the point he was making was that the measured diffusivity seems to line up with his model diffusivity from the young Earth model and not the old Earth model. And he's pointing out that there's a 10,000 factor difference, 100,000, sorry. And he made these claims that uniformitarian has totally failed this experimental test, and the data offer no hope for uniformitarian model. And to me, I took this somewhat as a challenge in that I wanted to see that if someone constructed a model more accurately, because I'd identified a number of flaws in the approach, but if those flaws were corrected, would it be possible to reconcile the data? So this is what I showed in 2008. And here I plotted the data differently simply because even Humphreys' approach in comparing the data had it was a bit problematic. And really, it's better to compare actual concentrations than to calculate a model diffusivity. But what I was able to show is that looking at the measured data, and this has taken account some of the measurement errors that Dr. Henke identified last week. If you take some of those into account, if you construct an old Earth model on sort of correct, with correct inputs, you can actually have very good agreement between the data. So there really is no paradox here. There is no reason to evoke something like nuclear decay, and there's no reason to insist that the Earth can only be 6,000 years old. So there's no scientific need to postulate an exotic physics phenomena to explain something that we can explain with ordinary physics. So what is different between my model and Humphreys' model? And this really is the crux of what we should be considering today. And I identified at least 4 major errors in the RATE model. One is they used a geometry that I thought was inconsistent with what they reported for the sizes of the data. They had a boundary condition that was inappropriate. They also used a wrong thermal history, and they misinterpreted the material properties. So pretty much just about they made an error in just about every aspect of the model. And when you assess sort of the magnitude of these errors, what I found is that errors 1 and 2 have a modest impact on the result, but errors 3 and 4 have a huge impact on the result. And that will be the focus today, the material properties and the thermal history, because the errors are of such a magnitude that they can account for this 100,000 factor difference. This is one of the things Humphreys claimed. He said the difference is so large that even small modeling errors should be inconsequential. And my counter argument is that at least 2 of your errors are not inconsequential. They are of very large magnitude. So we will talk about these 2 things. First, material properties of zircon, and then the thermal history of the site. And since Humphreys wasn't here to debate in person, I've tried as much as possible to pull his comments out of the few writings where he has addressed my work, and try and as best I can to portray what his position is side by side my position and give a response. So what Humphrey said in regard to my models is that in order to have that I okay, that the old Earth model can't be defended unless you can demonstrate both lower helium diffusivity and lower temperatures than in the past, than the model they used. And to set the context behind that statement, I had published some papers in the Journal of Creation, which showed that he made errors in the thermal history. And he said, well, yeah, but that's not enough to make a viable old Earth model. And I never said it was. I said, this is just one of multiple errors. So I agree with Humphreys on this point, that for there to be really a viable old Earth model, it requires both lower diffusivity and lower temperatures. And I'm willing to defend that position. And conversely, Humphreys now really has to defend his choice of either the higher diffusivity or the higher temperature. And an important note is Humphreys is actually tacitly now acknowledging there is an alternative. There is another model that if these two things can be demonstrated, there is a viable model. Okay, so let's talk about the helium diffusion properties of zircon. And I want to really dissect Humphreys' graph, because this is the iconic graph. This is that one picture that Humphreys will show over and over that is his vindication, his indisputable evidence of the validity of the rate argument. So what I'm starting with is the measured data. And if you look, most of the measured data taken at higher temperature falls along a certain line here. And for those who are not familiar with this kind of plot, it's an Arrhenius plot, which means you plot the log of some kind of quantity against the reciprocal of temperature. And the reason for doing that is if you get the data to fall on a slate line, it indicates an energy in the system. And that's an important energy that's required. It's a barrier energy that's required for a process, be it a chemical reaction or a diffusion, to take place. And if you look at this, most of this data falls along a high, the high temperature data falls along a line that goes like this, a fairly steep line. The creation model, on the other hand, most of it lies along a line that goes like this at a lower slope. And if you actually look at what Humphreys calls a very good agreement between his model and measurement data, it's not the majority of the data that agrees with the model. The majority of the data actually has a much higher slope. It's only these 4 data points that really fall close to the creation model. And that's important to remember, that he presents all this data, but really the argument stands or falls on just 4 data points. And these 4 data points at low temperature amount to only 8 parts per million of the total helium released during the course of this experiment. So that data, the reliability of that data needs to be considered. And what's also interesting is that if you extrapolate the high temperature data down to low temperature, it actually agrees much better with the old Earth uniformitarian model than the young Earth creation model. So really what is important to ask now is what is the validity of this low temperature data? The experiment that was, I'll go back a slide, the experiment that was done here, there is a paper back in 1966 by Fenton and Dr. They were looking at argon diffusion in minerals, but really the same methodology, mathematics apply. Very good paper. It's really the foundation of all of that experimental work. If you look at any of the published literature on these kind of diffusion experiments, this paper is always cited, I think without exception. And if you study that paper, you realize a few things. Number one is, technically speaking, in the course of the experiment, you do not measure the diffusivity. Diffusivity is not something that can be measured directly. It's not like there's a diffusometer they can just put in a sample and tell what the diffusivity is. The procedure behind the experiment is to take a sample, put it in basically a vacuum system, And the independent variables are time and temperature. So you adjust time, you adjust temperature, and for a given interval, you measure gas release. And then you keep stepping temperature and time however you wish and measure the gas at every step along the way. So really the raw data is temperature, time, and gas release. Nothing more. So then really the question is, how do you infer diffusivity from data where you just have temperature, time, and gas release? What Fettig and Kablitzer did is they assumed a model. So this is important. They assume a certain model for the system. And based upon that model, they came up with an equation where step by step at each point in the experiment, you can extract a number that would represent the diffusivity at that step, provided that the assumptions of the model were valid. And if the assumptions of the model are violated, then the number you obtain is not meaningful. And that's very important to note. And Fettig and Kablitzer talked about that at length, because it was a very practical paper. They studied a number of case studies, and they would show when the model breaks down and when it was valid. And their advice basically was that when you have deviations at low temperature, this is a region where the model is breaking down, that you should rather extrapolate from the high temperature part of the curve. Ignore the low temperature part of the curve, because if the model is breaking down there, the numbers that you're calculating are not meaningful. Yeah, you can put the gas release into the formula and get a number. It's not relevant to really the diffusion of the system. You should focus on the high temperature part of the data, because that is where the model is more likely to be valid. So basically, they advocate extrapolating from the high temperature data down to low temperature and ignoring the low temperature anomalies. That is how they recommend. That's best practice for using their method. Humphreys, on the other hand, and the RATE team, they tried to get data. They tried to get low temperature data repeatedly. And this is different than other people in the field that focus mostly on high temperature data, and for good reason, because it's a lot of work to get the data at low temperature because the gas release is so low. But if it's invalid anyway, why waste your time there? Focus on the high temperature data. So when the RATE, let's look at this table here. When the RATE study was published around, they first started publishing in 2004 and 2005, very little was known about helium diffusion zircon. Over the course of the last 12, 13 years, several researchers have studied the system. So we know a lot more about helium diffusion zircon today than we did back in 2004. And what I've done here is, from the data, you can extract a diffusion prefactor and an activation energy. And if you just look at the activation energy, and if you go back to this slope here from the low temperature data, you get a number around 13.9 kilocalories per mole. If you extract that activation energy from the high temperature data, which is what Fettig and Kablitzer say you should do, you get an activation energy of 38.1. Now, if I compare these two numbers from the RATE experiment to what's been published in the literature since then, Reiner's of 2004, activation energy 40.4. Cherniak, 34.9, 35.2. Wolf and Stockley, 38.2. And Gunther, you have 33, 39, and 38.9. So what you see is all of the activation energies that have been published are very consistent. What stands out is this low slope that comes from just 4 data points in their experiment, which Fettig and Kablitzer say should really be ignored because it's where their model is no longer valid. So the RATE team is placing tremendous significance on just 4 data points, and it's inconsistent with what everyone else in the field has been publishing. So just to reinforce this point, what Gunther did and the researchers, they studied, or they considered why there's some variation here in the diffusivity. And what you can see is that the diffusivity follows a trend based upon the alpha dose, how much damage, basically, accumulate damage in the crystal. And they are calculating this for a temperature of 180 degrees C. And what you can see that over a pretty wide range of damages, that the diffusivity is fairly flat. Now, if I plot these two numbers, if I take this as the activation energy and the diffusion and calculate the diffusivity at 180 degrees, I get 1.39, or 1.3 times 10 to the minus 19th, which plots right there. So their high temperature data plots right along where you'd expect it to. If you look at what they extract from the low temperature data, it is 2.5 orders of magnitude higher. It plots way above everybody else. And what's interesting is if you extrapolate this down to even lower temperatures, you're seeing diffusivities here, 5 times 10 to the minus 19, where everyone else is in the minus 24, minus 25 range. Now remember, Humphreys was saying, if I go back, how can you account for a factor of 100,000 difference between the model, the old Earth model, and the measured data? How can you account for that? Well, if you look at this table, it's pretty obvious. This is a fact. If I compare this number to that number, it's over a factor of 5 orders of magnitude. So this 5 order of magnitude difference is really manifested in just the difference in the diffusivity at low temperature. And you can see the number they use is much higher than everyone else's. And so really, okay, so let's move on with the debate. So one of the things Humphrey said was Loechelt knows about the above problem regarding higher diffusivities, but perhaps he's still hoping to solve it by writing many words and equations. Some years ago, he tried to publish a complex theory claiming that in situ zircons would leak much more slowly than in the laboratory, especially at low temperatures. So he's referring to my original paper. And I just want to point out, I wasn't just hoping to solve it. I did solve the equations. So then he criticizes me for not being peer-reviewed, and we'll talk about that later. But basically, I was rejected by the Creation Research Society quarterly, which I don't know how meaningful it is to say I was rejected by a young Earth creationist journal because I published something that didn't fit their beliefs. And going on, he said it's difficult for science journalists to see whether a complex theory might be concealing some hand waving. So he's objecting to the fact that my model is mathematically complicated. And my response to him simply is, don't dismiss my model without looking at it. Don't just say, because it's complex, it may have errors. If there's errors in it, then please point them out. I mean, he should be competent enough in mathematics to find that. And the final point, it might have been better had Loechelt performed experiments supporting his ideas. Well, the simple fact of the matter is I don't have the experimental resources to perform these experiments. But if experimental data is what we want to be judged upon, then my response is, then why can't we just go to the literature and accept the results of Reiners 2004, Cherniak 2009, Wolf and Stockley 2010, Gunther 2013. All of these papers contradict the helium diffusivity extracted from the low temperature data in the RATE experiment. So if he wants experimental data, I would just go to the existing literature and say, why can't we just use these results? What makes the RATE result so unique that it's different than what everyone else has published in the field? So as we start looking more at their data, though, there are some more surprises. So this is from a quote from the RATE book. says, after that, in the summer and the fall of 2002, we tried several times to get lower temperature zircon data. However, we only discovered several wrong ways to make such measurements. First, we asked the experimenter to do new runs on the same batch of zircons, but at lower temperatures. Once again, he's always trying to get lower temperature data. The results were ambiguous. An effect we decided was due to exhaustion of helium from the smaller zircons in the batch, thereby increasing the effective radius of the remaining part of the batch. So evidently, they ran several experiments, but the results are unpublished because, in his words, the results were ambiguous. But what does that mean, ambiguous? Presumably, it means it didn't support their hypothesis. But the fact that they ran experiments that didn't support their hypothesis is, in fact, significant because it shows that they have conflicting data, they have contrary data. And even if for some reason the results are invalid, at least publish the results so the rest of the world can judge and see whether, yeah, that data really does look to be invalid for some reason. They dismiss it by saying that helium was exhausted from the smaller zircons and that increased the effective radius of the remaining part of the batch. Essentially, that's his way of saying the diffusivities came out lower than what they wanted. That's his way of saying it. They ran experiments, the diffusivities came out lower than they wanted. It didn't support their model, and so because they think it's ambiguous, they dismiss it. And this is a concern because if they had experimental data that didn't support their hypothesis, it should be published. That's the scientifically proper way of doing things. You publish your data, the good and the bad, whether it supports your hypothesis or not. You publish the data. But it's not just the data they withheld. They did publish preliminary data from an experiment back in 2002. It was published in the 2000. Well, okay, so they published some data from 2002, and when they published that data, because they were not able to do the experiment themselves, they had to work with a third party, an external lab, to do the experiments. When they published the 2002 diffusion data, the experimenter's lab report was included. When they published their final data, there was no lab report from the lab, from the researcher. And that's not just an oversight. There was a young Earth creationist that I dialogued with on the Talk Rational blog, I guess you'd call it, or a discussion board. It was a discussion board. And I brought up this point that, look, Humphreys didn't publish lab report on the final experiment, but he did on the preliminary one. Why was that lab report missing? And this young Earth creationist basically said that, oh, everyone's suspicious, accusing Humphreys of withholding things. And to prove us all wrong, he said, I'll go approach Humphreys, ask for the lab report, and share it with everyone, and prove to you that all of your suspicions are unfounded. So this is what he said. I've begun a dialogue with Humphreys, and I did receive the lab report. Listen to this. The only way he would give it to me was if I promised not to give it to you or anyone else without his permission. I don't know why he's so tight with it. He seems to have some funny ideas about sharing information with non-young Earth creationists. He was real suspicious of me at first, quizzing me about my young Earth credentials and such. So the lab report exists, but he will not share it. And he's actually suspicious of people who want to see it. And my question is, what's in that lab report? Because if the researcher who published it quoted an activation energy or a closure temperature or anything like that, it would clearly show whether he used that low temperature part of the data or not. So that would be a direct indication of what the experimenter did. So let's talk a little bit about the experimenter then. And this is what was published by Humphreys in 2003. Through a small mining company, Zodiac Minerals and Manufacturing, we contracted with Kenneth A. Farley of the California Institute of Technology, Division of Geological and Planetary Sciences, to measure the diffusion coefficients of the zircon and biotite from the hematite. He is a recognized expert on helium diffusion measurements in minerals, having many publications related to that field. As we wished, Zodiac did not tell Farley that they were under contract to us, the goals of the project, or the sites of the samples. In other words, basically lie to get the data and use a third party to lie for you. But all the while, Kenneth Farley thinks he is working for a mining company, and then one day he goes to a conference and finds that the data that he took is published by Young Earth Creationists. Totally caught by surprise. And when I tried to contact Farley back in 2005, he did not want to talk much about it, but he had 13 words to say. I have a strong opinion. These people are totally dishonest. End of story. They lied to get the data. And what's also interesting is if you research the Zodiac Mineral and Manufacturing Company, there is a company by that name registered in Oregon City, Oregon. The officer is Majda al-Kutani, I guess. And there's no activity, no evidence of land holdings, no evidence that they ever mined or manufactured anything in their existence. But nevertheless, they were used to get the data. So this raises some concerns about the ethics of the study. Based upon the standards of many journals, what Humphreys did would be called plagiarism, because he published data that was taken by somebody else without that person's knowledge or permission. And in many journals, that would be considered plagiarism. So it undermines the credibility of the whole thing, considering that with what we know today, so much of the data in the field, in the literature, contradicts these 4 samples from the RATE study, and the history behind acquiring that data is now very suspect. Okay, so I have a few questions to ask Humphreys. He was unable to join us today, but said he would be following these presentations and giving his responses by email. So I'm going to line item my questions. First one is defend your extraction of the helium diffusivity using only 4 low temperature data points. When Fedek and Koblitzer advised extrapolating from the high temperature part of the curve. And then also defend the high helium diffusivity in light of all the other researchers, which they report diffusivity is over a factor of 100,000 lower. Also, why don't you release the unpublished RATE experimental data for critical review? And while you're at it, release the lab report so that we can review that as well. So these are things I guess if they want credibility behind their work, they need to address very basic questions like this regarding transparency of data reporting, responses to legitimate questions and things like this, if what they really seek is credibility. In the eyes of the secular community, these things would do a lot to promote that credibility. So I will move on now to talking about the thermal history of the site, which, like I said, is the second big error they committed in the modeling. And let me now give a little bit of history to the Fenton Hill site. Fenton Hill was the site of several exploratory wells that were drilled as part of the geothermal energy program. And the site is physically located on the southwest margin of a large volcanic structure called the Valles Caldera, and it erupted explosively about 1.25 million years ago. And if you're not familiar with caldera type eruptions, think of Crater Lake. If you've ever seen Crater Lake in Oregon, think of a volcanic eruption like that, but maybe 3 to 5 times bigger. So a very big eruption that pretty much destroyed whatever volcanic structure was there and left a big depression in the ground. So to this day, the area is very active geothermally, which is what attracted people's attention. Most of the exploratory geothermal wells were located inside the caldera. And that's because when the floor of the caldera collapsed, the bedrock fractured, and there was, it facilitated the circulation of water, which is a key part to a hydrothermal system. But like most places in the Southwest, water is pretty limited. So the question was, can we extract energy from other sources? In particular, it was an experiment called hot dry rock, which sort of says it all. Looking at rock that is hot, but it's dry. There's no groundwater flowing through it, so it's not a traditional hydrothermal system. So Fenton Hill was part of that the hot dry rock program. And it's unique in that it was located outside the caldera, not inside, but outside, where the Precambrian rock wasn't fractured. And that was important because they wanted impermeable rock. Basically, the idea was to drill 2 wells, frack between it, and force water through that to create an artificial hydrothermal system. But you wanted impermeable rock because otherwise you'd have water leaking, you'd pump water in and you'd never get it back out. So they wanted to make sure it was impermeable rock. And an important note is this site is not your average typical site. This is not a hole drilled in your backyard. This site was intentionally chosen to be a zone of high geothermal gradient. They were looking for hot, dry rock. So it's not a surprise that the temperature there is unusually high. And let's look at the valley caldera sort of schematically. This is the caldera, so this is the area that was collapsed. You have in the center the resurgent dome and some later eruptions that were around the margin. And you can see this is the part that was collapsed. And if you notice these the Baca well sites, a lot of these were some of the geothermal wells interior to the caldera. Fenton Hill is off to the side. And then you have a natural drainage of the caldera. It used to be a big lake, just like Crater Lake. It's filled in now, but you still have a stream flowing out through San Diego Canyon. And if you look at the heat flow, it's not symmetrical around the caldera. It's cool towards the east and the north, and it's high to the south. This is the direction of groundwater flow, and it parallels the direction of surface water flow through here. And you notice that this is a very high thermal gradient here around Fenton Hill. So you can see there's a lot of heat just going in that direction. So in order to model the thermal history, we need some data on what the past history was. So Humphreys and his RATE colleagues, they identified 3 papers that have become a focal point of the debate. So it's worth at least talking briefly about these 3 papers. The first one's by Kolstad and McGretchen from 1978. And some key features of what they did is they only used thermal data to constrain their model. And their basic model for why the temperature at Fenton Hill is so much hotter than the typical ground temperature in other places is they assume that when the volcano erupted over 1 million years ago, that a large magma chamber wasn't placed, and then heat flowed conductively from that magma chamber to the site. Problem was when they assumed when they did a parametric study, and when they had a magma chamber of radius 8 kilometers, they weren't able to replicate the temperature. So they eventually went to a 12-kilometer model, which could at least match the current temperature, but it required a magma chamber much larger than would have been reasonable. And to give you an idea, this arrow right here shows the current temperature at 3 kilometers, 197 degrees. And you can see their 3-kilometer model only peaks out somewhere here in the mid 150s. So it never even gets close really to that level, and it has a temperature that slowly rises and is relatively constant for a period of time. So that's the first reference. The second reference is by Harrison, Morgan, and Blackwell. Some key differences. It's a later paper. So 1986 is 8 years after 1978. So they have 8 more years of knowledge and data to work with, and including some argon age spectra. And that was Harrison's contribution. He's one of the foremost people on argon dating. So from that, they came to the conclusion that the heating event must have been more recent than 1 million years ago. And they bracketed it between 3 and 60,000 years based upon the argon data. Morgan and Blackwell were focused more on the thermal side of things. And together, Blackwell, I believe, did a lot of the modeling. They showed that they couldn't replicate the data, the thermal data, if they had a thermal event that was older than 40,000 years. So both the argon spectra and the thermal modeling independently support a date for this heating event that is more recent than the eruption of the volcano. And then to note, they also saw from the age spectra some thermal events in the Precambrian 870 million years ago and 1,030 million years ago. And this is a picture of the model from Harrison. The last paper is by Sasada. And this is interesting in that it's a very different technique. It's based upon fluid inclusion. And to be honest, I'm not that familiar with the whole methodology, but basically the idea is that if there's hydrothermal fluids captured in some of the minerals, that you can examine them and look at how they behave under temperature and pressure, and based upon that, infer at what temperature the fluids had to form, because basically things will equilibrate at a certain temperature, and then when it cools down, you'll have some phase separation. So you can get some interesting information on past temperature, but there's no time information. So it's only temperature. You have to have other independent data to infer anything about the timing. What they found, though, was really 2 thermal peaks, a thermal maximum here. This would have been over 200 degrees. And then they noticed that temperatures dropped and then rose again to present temperature. So they have a thermal pattern that is high, low, high. And they assigned this thermal maximum to the eruption of the Valley's caldera. But I just want to point out now that it is equally possible, considering that Harrison, Morgan, and Blackwell noted that there were these events in the age spectra, especially 130 million years ago, or 1,030 million years ago at 200 degrees C, that this thermal maximum could easily correlate with these events and not the eruption of the Valles caldera. So let's talk now about the model. So this was the data that Humphreys had in hand, and this is how he used it. So he said, in the RATE book, we outlined a simple model appropriate for the uniformitarian view. Steady state, low rate radioactive decay, helium production, and diffusion for 1.5 billion years at today's temperature in the formation. So he basically took today's temperature, let's say 197 degrees at 2.9 kilometers well depth, and treated it as a constant overall time. And that's his view of uniformitarianism. And this is something that really comes out in Humphreys' approach. His view of uniformitarianism is that it's constant, things don't change, which is really not the view of practicing geologists. It's that my working definition is that the structures that we can see today can be explained by the processes we observe today operating over time. It doesn't mean things are constant, because we see changes today, and sometimes they're not slow changes. When a volcano erupts, it's not a small change. When there's a major earthquake, it's not a small change. It's just the cumulative effect of those changes can explain what we observe today. So my point is that a constant temperature is very inappropriate, and really is artificially handicaps the old Earth model, because you would not expect today's high temperature to have been sustained over the past indefinitely. So you can see the difference between the rate thermal model, which is just a constant, and my model. And you notice my model is not a simple function. It's not a line, a parabola, an exponential decay, because I'm not trying to assume a simple functional form. What I really tried to do, and I'm not going to go through this in detail, but you can understand the thought process at least. I tried to go through the literature and find what were the major geological events at different time periods, looking at the stratigraphy, different formations, either at Fenton Hill or the surrounding area, because many of the rock layers might be missing here, but they are found in adjacent areas. And based upon this, construct a thermal model. So two very different views. Do you keep temperatures today constant through all time, or do you try and follow the actual geologic history? So here is Humphreys' defense of their constant temperature model. Our assumption of constant temperatures is generous to the uniformitarian model. Okay, so he's saying this is actually generous. It's actually a lower bound to the temperatures, because he said later studies, Harrison et al., added a more recent pulse of heat, and this is important, and have past temperatures being higher, 110 to 190 degrees more than today's level just 24,000 years ago, and higher after that. So, and he's referring to Harrison, so he's referring to this graph. So let's try and understand this graph, and I'll just pick the curve at 2.9 kilometers as an example. 110 degrees more than today's level. So this is 87 degrees here. That is 197. So the difference between here and here is 110 degrees. So I agree, the difference between here and here is 110 degrees. And he said this was 24,000 years ago. So his interpretation is this 24,000 years is 24,000 years in the past. And he says, and it was higher before that. So presumably he's just looking at this curve and notices there's a slope here. And if you just imagine the extrapolation, it would go up further. So that's how he explains temperatures. Past temperatures were 110 degrees higher than today's temperatures 24,000 years ago. And he keeps reiterating this point, past temperatures were higher. But here's the problem, and I'll show you. This is Humphreys' interpretation on the direction of time. What is past, what is present? This is my interpretation of the graph. I interpret the arrow of time pointing the opposite direction. I basically claim Humphreys read the graph backwards, and here's why. Because if you look at the text of the paper by Harrison, Morgan, and Blackwell, they said that in the beginning of their model, they had a geothermal gradient of 30 degrees C per kilometer. If you look at a depth of 2.9 meters, that gives you 87 degrees. So 87 here matches their initial condition of a 30 degrees C per kilometer geothermal gradient and a depth of 2.9 meters. 2.9 times 30 gives you 87. That's the starting point. Furthermore, we know the temperature today at 2.9 kilometers. It's 197 degrees. So all you have to do is look on this curve. Where do you see 197 degrees? And it's at this point, 24,000 years. And if this is the current temperature, you can just look across and you can see this curve never goes above 197 degrees. It's always less than it. So this is a very different interpretation. Does time go this way and you have past temperatures being higher in the past? Or does time go this way and you have past temperatures being lower than the past? Because remember, in my model, I'm trying to actually put in these actual time and temperature points to have a temperature varying model. Humphreys is trying to defend a constant temperature model, but his defense for doing that is that it's at least a lower bound because past temperatures were higher. But if this interpretation of the graph is correct, past temperatures are lower. And that means it's no longer valid to use a constant temperature even as an upper bound. So when I had this kind of information, I thought it would be good to publish an article in the Creation Research Society Quarterly, because they published Humphreys' paper in 2004, and seeing that by this time I had modeling results, I had evidence that he interpreted a graph incorrectly, and I thought this was a legitimate opportunity to go into their forum, into their journals, and engage in a dialogue there. And so after a long period of time, this was almost a year-long process trying to get my manuscript through review. Eugene Chaffin was the section editor. And when I started to point out this error by Humphreys in reading a graph backwards, Chaffin replied that in a previous communication, I suggested that you read page 52 of the RATE 2 book again. On that page, an expanded discussion is given of the statement from the Creation Research Society quarterly article of 2004, which you quoted above. By the way, the paragraph you quoted was repeated in the RATE book. 3 different editors and several reviewers have not questioned the accuracy of that statement to my knowledge. So basically, the dialogue with the editor was something like this. I said, Humphreys misinterpreted the thermal history. If you go back to the original paper, look at what's said, and look at the graph, it's inconsistent with what he wrote. And Eugene Chaffin basically said, what Humphreys wrote was correct, and it's been reviewed. Go back and read what he wrote, and he'd never bothered to even check the original reference. Basically, Humphreys wrote it. I'm misunderstanding Humphreys, and there's no point going back to the original paper. It's correct. 3 different editors and several reviewers have not questioned the accuracy of the statement, so it must be correct. I kept persisting on this matter, and eventually Chaffin just rejected the paper. And this was his final comment. He said, thank you very much for the phone conversation today. It's apparent that we must agree to disagree upon some issues raised in the manuscript Fenton Hill revisited, so forth. My opinion is that this manuscript has unrealistic temperature profiles, which then lead to unrealistic values of the diffusion constants. Hence, I conclude that I cannot accept the manuscript for publication without significant changes. So just to go back here, what he's saying is this constant temperature used by Humphreys is realistic because he published it. He was the editor when the other paper was published, so he published it. So this was considered realistic. Something like this was considered unrealistic. Now, granted, I had a more simplistic model at that time. It was a little bit more box-like. It didn't have some of this fine detail here, but I had a peak here, I had a flat section, I had some steps here. So it was more box-like. I didn't have all the details. But he said he's rejecting the manuscript on the grounds that I'm using an unrealistic temperature history, whereas Humphreys used a realistic one by keeping it constant at today's temperatures. So not getting through the journal, eventually I ended up publishing my work online. And eventually Humphrey saw that and responded also on a website. And this is his comment about my publishing. He said, even on temperatures, Loechelt shows a remarkable ability to misunderstand the experts. So not only did I misunderstand the experts, my ability to misunderstand is remarkable. It's not just ordinary misunderstanding, it's remarkable misunderstanding. He, being Loechelt, fails to grasp the essence of the published Los Alamos heat flow models, which is that due to nearby volcanic activity in the past, they imagine, temperatures in our borehole would have been higher than today for hundreds of millennia. Instead, Loechelt insists temperatures were always lower. And then, with confidence, he says, as for me, the critics have increased my confidence. My feeling after working through each criticism has been, is that the best they can do? They must not have been able to find a real error of any importance. That's Humphreys in 2008. So he went on to publish something very similar in the Journal of Creation. Almost took verbatim what he published on a website in a journal, which again is kind of interesting. Typically you don't double publish, but I think the rules are a little bit different for the Journal of Creation. And in any event, because he published in the journal, I had now another opportunity to point out my concerns. So I wrote a letter to the Journal of Creation, again, pointing out the fact that Humphreys read a key graph, or several graphs, but he read his graphs backwards. I was trying to make that point in 2006 to the Creation Research Society Quarterly. The editor refused to accept that. I published online. Humphreys absolutely refuted that. And so I tried a third time, now in the Journal of Creation, in a letter, where I made the point again, Humphreys read his graph backwards. And for the first time, he concedes. He says, Loechelt's letter, points out an error of mine, for which I'm grateful. So he actually conceded this point. But then he goes on, however, as this reply will show, the helium data continues to support the short biblical timescale just as strongly as before. So even though he did make a mistake, I guess he considers it a mistake that's not of any real importance, because he is confident that the evidence is just as strong. And so evidently reading a graph forwards or backwards and having temperatures higher or lower is not of any real importance, even though I've showed in my model otherwise. So let's talk about this error, because this is now really the first time Humphreys has admitted that he made a mistake here. So let's see what he said. He said, I did not read the Harrison paper, carefully. I was reading the graph backwards. So he agrees. He read the graph backwards. So now my comment is that's an interesting confession. And considering the importance of the RATE study to the young Earth community, I'm surprised that all the attention and all the publicity that the RATE study got, no one bothered to read the paper closely enough to see whether it was forwards or backwards. Not Humphreys, not the reviewers, not the editors. Even after I point out to the editors the error, they don't investigate. And then Humphreys' next statement is, instead, the Harrison graph, asserts that about 20,000 years ago, the temperature at 2.9 kilometer depth started rising from an 87-degree baseline up to the temperature today, 197 degrees. Okay, so that's an interesting confession as well. But if Harrison, Morgan, and Blackwell are right, then I've demonstrated the second point in this debate. The first point being that I had to demonstrate lower diffusivity. And I showed, if nothing else, that 4 different papers published on that subject all had lower diffusivities than what Humphreys used in his RATE model. So the second point I have to demonstrate is that there were lower temperatures in the past. And Humphreys is basically admitting, yes, if the Harrison, Morgan, and Blackwell paper is correct, temperatures really were lower, and by quite a bit, not too long ago. And really, this is a devastating blow to the rate study. They don't admit it as such, but if this one paper is correct, it basically invalidates everything they did. If this one paper is correct, so what does well, let's talk about this now. So now that there's an error and it's admitted, this is not a point of debate. Humphreys' own words, he read the graph backwards. His own words, the Harrison, Morgan, Blackwell paper does have lower temperatures to 20,000 years ago. Three things I note. One is it exposes an error in their logic. And the headline message of the RATE team is that the zircons from the Fenton Hill wells could only retain the helium for thousands, not billions of years at today's temperatures. And I put thousands, not billions in quotes, because that is actually the title of a book, a popular book on the RATE study, Thousands, Not Billions, by Young. So their headline message for this study is that the zircons could not retain their helium, could only retain their helium for thousands and not billions of years at today's temperatures. And then they extrapolate that if that's the case, then the entire universe can only be thousands and not billions of years old. But there's another possibility. Suppose the headline statement is correct. Suppose it's true that the zircons can't retain their helium at today's temperatures for billions of years, for only thousands of years. Maybe the temperatures at the site have only been this high for thousands of years. That's another possibility, equally valid possibility, that maybe it's not the universe that's 1,000 years old, it's just the heating event at Fenton Hill that's 1,000 years old. They overlook the possibility that this may just be a local phenomenon at the site and not a cosmic phenomenon. What makes it more compelling is that's not only just a logical alternative, that is actually what one of the papers says. Taken at face value, that is exactly what Harrison, Morgan, and Blackwell say. They say that the heating event was recent. And this was published long before the RATE study. So they can't claim this was some after-the-fact response to their study. This was published before the RATE study even began. And had they understood that paper, they would have realized that this was a very bad site to select for testing a young Earth hypothesis. It was a poor selection of sites, because how do you separate this as evidence for a 6,000-year-old Earth when some other researchers say it's a 20,000-year-old heating event? Hard to separate those two. And what makes it even worse, they had cited this paper and they had completely overlooked its implications. And then the third point is why'd they overlook it? And I believe it's because they had a very strong bias. And if you look at, they read into the Harrison paper what they expected to find. They had, I think, already latched onto the thought that past temperatures were higher. They saw a curve that was low on one side, high on the other side, and they said, aha, we have evidence. They didn't really read the paper. And conversely, to the credit of Harrison and his co-authors, the prevailing view when they published was that the temperatures at Fenton Hill were from the eruption of the volcano 1 million years ago. And they proposed a thermal history that really was a little bit counterintuitive at first. But they defended based upon their evaluation of the data. So their conclusion was based upon really looking at the data objectively. And to the credit of the secular scientific world, other researchers accepted the conclusions of the Harrison paper. they didn't have this preconceived notion that the heating must fit to some canonical timescale. And if there's evidence showing that the heating event was 20,000 years old, they were willing to accept that in the absence of conflicting data. So this is really a big blow to the whole helium diffusion study. And what is Humphreys doing for damage control? So what he basically has to do, he has to either discredit or diminish the Harrison paper as much as possible. You can't take that at face value. Because remember, his quote is, "Our assumption of constant temperatures is generous to the uniformitarian model." And that's hard to defend if a paper, which Humphreys now agrees, states that 20,000 years ago, it was more than 100 degrees cooler. So instead, he's relying very heavily on the Kolstad and McGretchen paper, because the heating event in that paper starts 1,000,000 years ago, not 20,000 years ago. The point is, both cannot be right simultaneously. And here's a case where in the literature we find two conflicting papers, two conflicting models. And really, you shouldn't pick which paper, you shouldn't pick the paper based entirely on which one's favorable to your model or your hypothesis. You should really put them side by side and say objectively which one matches the available data better. Especially now, in hindsight, we have more data to evaluate these papers than the authors did when they published it. And so really what Humphrey should do, and what I'm going to try and do today, is really decide between these two papers based upon the available data. But it's true, the Kolstad-McGretchen paper is more useful in supporting Humphrey's cause. And then there's the third paper, Sasada. So what Humphreys does is he uses that in the framework of the Kolstad-McGretchen paper and uses it to fine-tune some things. But one thing to keep in mind with the Sasada paper is it has no chronological constraints. It's temperature only. And in order for that paper to be useful at all, you have to make some assumptions on the timing of the thermal events. So this is what came out of this. Humphrey's response was to come up with a new temperature model. And this is how he justifies it. And he calls it the best uniformitarian picture of temperature history. So again, he starts with Kolstad-McGretchen. The basic model of Kolstad-McGretchen would probably give Sasada's broad 230-degree maximum at 2.6 kilometers depth if we were to use a magma chamber radius somewhere between 8 and 12 kilometers, say 9 or 10. So he's just now started guessing on things, okay, trying to fit these curves. We could guess that at a 3 kilometer radius, the model's temperature curve would look much like the solid 12 kilometer radius model line for a depth of 12 kilometers. So basically saying, well, I want a magma chamber, say 8 or 9 kilometers. I don't have any data for that. Kolstad-McGretchen never studied that, but they did do a 12 kilometer model. So maybe 12 kilometers at 2 kilometer depth would be the same as 8 or 9 kilometers radius at 3 kilometers depth. We're just kind of, we're guessing, basically. He says we're guessing. And then he tries to fit Harrison into that and say there's only a real small temperature increase. And then his last statement, if I were uniformitarian, so this is his view of how the secular world or the conventional geological world would view things. Here's how he puts the papers together. Humphrey says temperatures rose to a broad maximum, say about 250 degrees C, about 0.9 million years ago, declining slowly to minimum about 170, 20,000 years ago, and then rising rapidly today at 197. So this is how he can get away with still saying, well, temperatures in the past were higher than today. Well, and they dropped a little bit, but not much, but overall they were higher. So he's still trying to defend that notion. Okay, so how does Humphreys try and dismiss the Harrison paper? So this is what he says. as I focused on the 1986 article, I saw that it appeared to ignore the heat that a nearby volcano would have provided to the borehole during the last alleged 1 million years since its last ash eruption. Then this seemed quite odd to me, especially since a 1978 study by the author's Los Alamos colleagues, Kolstad and McGretchen, showed that the nearby volcano would heat the borehole up to within 50 degrees of today's temperature, maintaining that high temperature for allegedly the last 0.8 million years. And then finally, why did they ignore the volcano? So really, this is his dismissal of the Harrison paper. They really ignored the volcano, as if they didn't realize there was a volcano nearby, as if they had never considered it. Let's go to what Harrison, Morgan, and Blackwell actually said about this Kolstad and McGretchen study. They said Kolstad and McGretchen postulated that high temperatures at this site were caused by conductive cooling of a major subcaldera magma chamber in place about 1 million years ago. The postulated magma chamber extended well beyond the caldera margin, with its top at a depth of about 3 kilometers, just below the maximum depth of initial drilling at the Fenton Hill site. The argon age spectrum results and the new temperature data suggest that the age of the heating event at the Fenton Hill site should be revised. So they didn't ignore the volcano. They were very aware of the study of Kolstad and McGretchen. Their point is they have new data. They have argon age spectrum data, and they have additional temperature data. And the Kolstad model no longer fits the new data. So they didn't ignore the volcano. Well, let's see what Kolstad and McGretchen said, or what Humphrey said about the Kolstad and McGretchen paper. And this description here. The 12-kilometer model, the solid lines in the figure, has a temperature at 3-kilometer depth being over 800 degrees a million years ago, and then decreasing gradually to the 200 degrees observed today. So this model claims higher past temperatures than today. Again, he's trying to find supporting evidence for defending his constant temperature model. And his argument is that past temperatures were higher than today. The subtle thing that he has done here, and you have to read his writings carefully, is this is not the argument he made in the RATE book. He used a different figure, he used a different model, which did not support his conclusion. And the reason is he read that graph backwards too. He read the graph in Kolstad and McGretchen backwards too. And I pointed that out, but he did not acknowledge that. But what he has done, he abandoned his original argument and went with a different model, a different graph. So what's fascinating here is because he abandoned his original argument, he's tacitly conceding that it was not a defensible position. But rather than revising his conclusion, he's looking for a different figure in the paper to support his conclusion. But at least he's reading the graph the right way. And I think we're making progress as far as this debate between Humphreys and me. He is making progress because at least he's reading the graphs correctly. And I give him some credit for that. So here's the thing, though. He's also acknowledging that in order to count for higher temperatures, if it really is from this magma chamber, it has to be larger than 8 kilometers. And he's proposing something 9 to 10 kilometers in radius and 3 kilometers deep. So a simple test is, have we found evidence for a magma chamber of these dimensions? His model now requires a certain geometry and dimension for this magma chamber. Look at these quotes. Subsequent drilling at Fenton Hill to a depth of almost 4.4 kilometers has not encountered a recently crystallized intrusion. So at least at the radius of Fenton Hill, it wasn't found. Now, by the way, Fenton Hill is at about 11 kilometers. So by proposing 9 or 10, he just barely avoids that. but he can't avoid the Nielsen paper. Nielsen did a very exhaustive study of the stratigraphy inside the caldera, Redondo Peak, and that whole thing, and really reviewed all of the well data and trying to reconstruct the underground stratigraphy. One of the results of our study, this is Nielsen now, was surprising. So this surprised them, was that the deep drilling failed to intersect any intrusive body that could be considered the cause of the resurgent doming. Basically, not only did they not find a magma chamber at 11 kilometers, they didn't find one even in the very center of the caldera, which is surprising because you'd expect for something like that, there would have to be a magma chamber somewhere to account for the eruption. But it evidently did not show up in any wells drilled to a depth of 3 to 4 kilometers. So Nielsen, they began to think maybe it's much deeper than everyone suspected. And so they did a calculation based upon the doming and everything. They arrived at a depth of 4.7 kilometers. So it was deeper than anyone imagined. And now let's talk about the Sasada paper. So Sasada basically associates the thermal maximum at 230 degrees with the heating from the magma reservoir, which erupted the Bandelier Tuff. He cites a reference putting the latest eruption at 1.12 million years ago, a little bit earlier than Kolstad McGretchen's age of 1.04 million years ago. So he is associating this thermal maximum of Sasada with the eruption of the volcano, which in fact Sasada himself did. But we have to look closely of the supporting evidence. Sasada made that statement but gave no proof. It was an opinion, but not really a hard conclusion because there's no supporting data. The thing to consider, though, is given the long history of the rocks at this site, the thermal maximum could have happened in the Precambrian and not the Pleistocene. So there is another alternative. And that really was suggested by the Harrison paper again, because they showed that in the age spectra, the argon age spectra, that there were thermal disturbances at 870 million years ago and 1,030 million years ago in that same temperature range. And then Laughlin, I just said that. But Laughlin also said hydrothermal fluids were probably present during the two tectonic events accompanied by magmatism, i.e. during Precambrian and late Cenozoic times. So Laughlin, and in that paper was a very extensive study of the geology of the Fenton Hill site. They acknowledged that there was hydrothermal fluids, that is what Sasada was studying, and that they could have come from both either the Precambrian or the Cenozoic. And let's just talk a little bit more about this, the Precambrian part, because this part of the geology was not discussed very thoroughly. I won't, I know this is going long. I won't go through all the details here. But what you find is, if you start looking at the Precambrian geology now on a continental scale, plate tectonic scale, well, you find this region of New Mexico, and Fenton, if you do this is the United States. If you don't recognize the outline, if I zoom in here, you can see Four Corners, Arizona, Utah, Colorado, New Mexico here. This is Fenton Hill. It's in the region of the Mesozoic orogeny, and the major geologic events are the orogeny, which is probably what created a lot of these gneisses that Dr. Henke talked about last week. And there are also some intrusion events. And if you look at what Brookings showed, that the dates of these events for the gneisses and for the intrusions fit the scheme. So the point is, there were some very large magmatic events that affected this site in the Precambrian, which very likely were the source of the hydrothermal fluids that were studied by Sasada. So there is good evidence to put that thermal maximum of Cicada in the Precambrian and not the Cenozoic. So I have some questions again for Humphreys. And this is regarding the Cicada paper. Okay. So Humphreys made the claim that the temperature cannot change much for the 6,000-year-old young Earth model. Now, he assumes a constant temperature for the old Earth model, which I say is inappropriate. But at 6,000 years, I agree. It's hard to imagine the temperature changing much over that time scale. But then how does he reconcile his young Earth model with Cicada? Because it says you have to have a high, low, high temperature. And that can be accommodated in the old Earth model, with the high being in the Precambrian, the low being in the Paleozoic and the Mesozoic, and the second high being in the late Cenozoic. That fits very well. But how does he interpret Cicada in a young Earth model where the temperature can't change over 6,000 years? And then the second, oh, and by the way, I pointed this out in one of my papers to him in 2012, and he never addressed it. So I want to bring it to his attention again. And he basically neglects using the Cicada data as a constraint on the young Earth model. He only applies it to the old Earth model. And this, I won't talk too much about this slide, but this is my response to his previous letter that I wrote in the Journal of Creation in 2012, basically pointing out that his synthesis of these three thermal histories is really just eyeball interpolation. There's no mathematical rigor at all behind it. When I see words like we can imagine that, or let's say the magma chamber is 9 to 10 kilometers, or one could guess the curve would look like, this is not mathematically rigorous to me. It is very, very conceptual. But more importantly, his model requires this magma chamber to be a certain dimension. And if you look at the studies that I investigated that tried to identify the dimensions of that magma chamber, it's not anywhere near to what Humphrey needs for his model to work. As I put it, it's smaller, deeper, and cooler than the one he proposed. So really, this data invalidates his thermal model. But we can learn something from this. And what we can learn is that heat conduction is a slow process. And a large magma chamber was required to account for the temperatures. And yet, that magma chamber was not found. So it's really hard to count for the present high temperatures because of a magma chamber directly. And also, the heat source must be fairly close. That's because only by bringing the heat source in close proximity to the well site can you actually get the high temperatures. And the third point is, all of the discussion Humphreys has made has focused around the magma chamber for the caldera. The hydrothermal system has not received much attention. And yet, if you think about it, the hydrothermal system is what attracted the research to the site in the first place, because they were trying to develop it as a source of geothermal energy. So really, I think there's something to be learned from studying the hydrothermal system. And this is a picture from Goff and Gardner and a bunch of others. The arrows here show the flow of the hydrothermal system. You can see the basic outline of the caldera, the wells in the center of the caldera, and then the water flow. And one thing to remember is, inside the fracture zone, the volcano floor collapsed, fracturing the rock, making it very permeable to groundwater flow. So groundwater can flow pretty easily inside this dotted ring. Outside, we know from Fenton Hill the rock is fairly impermeable. Remember, they were looking for hot, dry rock, and one of the important criteria was not just the hotness of the rock, but the dryness of the rock. So this is not a place where the water can escape. where the hydrothermal system drains is along the Hemis fault, because that was a pre-existing fault, and that connects the fractured rock in the ring system with the outside. So the primary hydrothermal system flows in this direction. And if you look at it, Fenton Hill is really outside the main path. But what Goff and company noted was that there was a second branch of the hydrothermal system flowing in this direction. But there's no outlet here. This part of the hydrothermal system has a natural outlet. This part of the hydrothermal system has no outlet. So once water reaches this point, it hits a wall of impermeable rock, and it can't flow any farther. So presumably it eventually has to work its way back out here. This is the drain. This is the drain of the system. If you look at the geothermal gradients, you can see in this direction, the directions here is basically going north, this direction, and then west. So as you go north, the subsurface temperature is high in the Hemis fault zone because this is the drain of the hydrothermal system. You get outside the fault zone, subsurface temperature drops. But once you start going this direction back in, it rises very suddenly. So it shows there's a lot of hot water near the surface right about there. Not a magma chamber, just a lot of very hot water close to the surface, right at the edge of the ring fracture system. Okay. So my point was to Humphreys that the source of the heating was not the magma chamber. It was the hydrothermal system. And because of that, it is not tied directly to the eruption of the volcano. And that would explain why it would have a different time scale than the age of the volcano, which is what Harrison said. So this is his response to that. Okay. He, Loechelt, apparently does not realize that the hot water had to have begun flowing at the time of the enormous main eruptions an alleged million years ago or so. And that thus today's high temperature at the RATE borehole site probably started soon after the two main eruptions. So two things to note here. One is he's abandoning his best uniformitarian model. Remember his original thermal model that he published in the RATE book, he abandoned because I demonstrated that he was reading graphs backwards. So then he tried to create a hybrid model using pieces of the other graphs and presenting that as his model. And then I showed that there was data falsifying that because his hybrid best uniformitarian model required a magma chamber of a certain size that physically has not been found. So it's been invalidated. So now he is no longer defending his best uniformitarian model. He's abandoned it again and now proposing a hydrothermal model and says, well, even if you rely upon a hydrothermal model, it's going to have the same age as the volcano. What's interesting is he proposes his hydrothermal model without any references, without any substantiating data. It is really just pure speculation on his part. And like so many of the things that Humphreys does, he oversimplifies things. So let's look at what researchers really have learned about the hydrothermal system. First, from the Goff paper. At Valles Caldera, dates on travertine deposits formed at hot springs discharging from the outflow plume, indicating an age of about 1 million years for initiation of lateral flow, although the dates indicate at least 3 distinct episodes. So the point is, if you look downstream, travertine deposits would be Soda Dam and some of these other surface springs. What he's saying is, yes, evidence from these deposits say that this branch of the hydrothermal system probably was operating for about 1 million years. So in one sense, Humphreys is right that some parts of the hydrothermal system probably do date all the way back to just after the eruption. But then look at the point Harrison makes. the thermal history deduced at this site is only applicable to the Fenton Hill site. Emphasize that. Only that site, not the whole volcano, not the whole region, only that particular site. It's not only very recent, it's very localized. And to support that conclusion, they make the statement, one sample from a deep well within the caldera has yielded a disturbed and highly outgassed argon age spectrum indicative of long-term heating. Well, Goff said that parts of the hydrothermal system did form 1 million years ago. Harrison says they found age spectra that indicate long-term heating. They were talking about Baca 12, right in the middle of the primary branch of the system. Now, here's the money quote from Goff. Hydrothermal outflow plumes can be long-lived features, but can evolve rapidly after magmatic and tectonic perturbations. So what he is saying is, yes, you can have a branch of a hydrothermal system long-lived like this, but a secondary branch like this can change and change relatively quickly because it's just flowing hot water. So the picture is this branch of the system is 1 million years old. This branch of the system is more recent. And all it would take would be some magmatic and tectonic perturbance to create that branch and change the groundwater flow. Now the question would be, is there any evidence of a geologic event that could account for this? Because in the end, geologists always like to eventually trace things down to measurable events. So there was after the main eruption of the Valles caldera, there were subsequent eruptions around the rim, around the perimeter, and most of them started in the north. But then there were some in the south. The latest one was called the Banco Bonito eruption, and it's this area right here. Recent dating of that is 35 to 40,000 years old, and it represents the youngest volcanic activity in the caldera. So there is a geologic event in the time frame that Harrison, Morgan, and Blackwell said the heating in Fenton Hill occurred. And what's interesting is, unlike the other eruptions here, which were in the upper part of the caldera, this was in the drain. So all that had to happen was for this eruption to disrupt the groundwater flow, thereby creating a secondary branch of the hydrothermal system that would flow in this direction. And because it would hit the impermeable wall of the caldera, it couldn't flow much farther, and it would have to sort of build up this wall of hot water along the side. So originally, groundwater flow could have been in this direction, and then the Banco Bonito eruption clogs the drain, so to speak. A secondary branch forms, and that explains the recent heating of the site. So that ties things back to a identified geological event. And I just want to show you the big picture. These were photographs. Well, this is a satellite, but this is a photograph that I took in 2011 from this viewpoint. Fenton Hill, for reference, is right here. So San Diego Canyon is highway number 4, is along highway number 4, and then take the branch highway 126 up to this viewpoint. You can see basically the edge of the caldera there, Redondo Peak. The main hydrothermal system would flow somewhere through here. Notice this big ridge here. This is the Banco Bonito flow. So it did really clog the drain. And then all that has to happen is now for another branch of the hydrothermal system to start flowing in this direction, and it would cause heating about here, and that heat is spread to Fenton Hill, which is very nearby. So that is my explanation for the thermal history of the site. Now, Humphreys did have a chance to to provide some comments in advance of this debate, even though he was not able to come here personally. So what I want to do is at least address the one question that he identified. And that basically is, and I'll just read it. We published the 6,000-year model, the red diamonds, in the year 2000. The experimenter, not knowing what answer we wanted, produced the blue data dots on the graph in 2003. The close fit of the model and the experiment is strong evidence that both are essentially correct because the probability of an accidental fit is low. So that's what he wrote in 2008. And 10 years later, he says, as far as I know, none of the Helium project critics have addressed that improbability. Do they think that rate was just lucky? Okay, so Humphreys did not acknowledge that after he published this in 2008, I wrote a response online in 2009, and this is from pages 5 and 7, and I add some emphasis. So this is what I wrote in response to his comment in 2008. I said, the apparently remarkable agreement between model and experiment is not remarkable at all once it is realized that the data was, number one, anticipated from the extrapolation of the earlier data. The agreement of the rate model is even less impressive when one considers that, number two, the model was artificially tuned to match a desired result, and that, number three, they never published the results of any of their intermediate experiments. I wrote this in 2009, and even though it's been out there now for 9 years, it's never been acknowledged by Humphreys. And he can't claim he's never seen it because when I published my paper, my letter to the Journal of Creation in 2010, I mentioned in a footnote I had previously informed Humphreys of this reply through Creation Ministries International in May of 2009. So after I published this, May of 2009, I informed them, I asked them, please let Humphreys know that I've responded to his question. I said, please let him know, here is a link to the website. So Humphreys cannot say that no one has answered his question. So in his response to my letter, he acknowledges that he got my email. He says, as he mentioned, on May 18th, 2009, he sent an email to the editors of this journal, merely giving links to his 2 articles. For him to pull the full text, so I'm not sure why he says merely giving a link. The editors forwarded to me, asked if I wanted to reply on the Creation Ministry International website or the Journal of Creation. However, my early reply, this reference to the same issue, seems to be quite adequate. So he says in his early reply, no one has answered his question. I come back less than a year later saying, I've answered your question, and please let Humphreys know, here is a link to my paper. He says, thank you, I acknowledge that, but what I said originally is still adequate. So he did not take my response seriously. But let's walk through it real fast. So the first point is that the RATE teams published a book in 2000. And this was sort of like, they had 2 books. The first book was sort of the pre-study book. It outlined the studies they wanted to do, why they wanted to do it, and published any preliminary data they had, mostly just to justify the research program and to and for publicity, letting people know. The second book was the follow-up with the results of the study. So in the first book, Humphreys thought that the diffusivity of helium in zircon was higher than that of biotite. And he created a model where basically the zircon sphere was a hollow shell or a hollow sphere surrounded by a biotite shell. And he treated the helium inside like it was a free gas. When they actually got experimental data, they got data for both zircon and biotite. And when they did, they found out that biotite actually had a much higher diffusivity than the zircon. So really, the 2000 model was wrong. So that's why Humphreys talks about the new creation model as opposed to the old one. The new one took into account the fact that the zircon diffusivity was lower. But what's interesting is rather than just leaving the model a bare zircon model, he still kept the biotite shell, but he equated the diffusivity to that of zircon, even though it's considerably different. Now he says he matches the data very well. And I question that statement fundamentally, because if he means just the helium or just the zircon diffusion data, that's one thing. But since his model has both the zircon and the biotite, you have to consider how well it matches the biotite diffusivity data, and it doesn't match it well at all, because he's assuming that this and that are equal in his model, even though his own data shows it's not. So that's a point. So I'm going to go through some of the things. How does he justify this model? Okay. So as we mentioned, I'm reading here, as we mentioned at the end of section 4 in our first creation model, we wrongly assumed that the zircons were a negligible impediment to the helium diffusion. In this section, we construct a new model. So basically, he's acknowledging his first model was wrong. So anything he claims about his 2000 model is wrong, because it's based upon a wrong assumption. And then he says this: because the biotite diffusion coefficients are not too different from the zircon coefficients, we should have a model accounting for two materials. Okay, that's somewhat reasonable, but I would say that the diffusivity of helium is so much higher in biotite than zircon that really, to first order, you could ignore the biotite altogether and just use a bare zircon model. But if you really want to model a two material system, okay, I'm not opposed to that. I'm just saying it's probably not necessary. And so then he says, in 1945, R.P. Bell published such a solution for the corresponding problem in heat flow. His solution, which is mathematically complex, allowed for two different diffusion coefficients in the two regions. Okay, so he's found a model for a two material system. And then he says, we will simplify the solution considerably by making the diffusion coefficients the same in both regions. And this is just one of those shocking statements. I just say, what? He presents data showing that the diffusivity of helium in biotite is an order of magnitude higher than zircon. Then he identifies a model that's appropriate for a two material system. And then he simplifies that model by making the diffusivity in the two regions the same, which basically means you don't even need the two material model. And that's to me unbelievable, because if he's identified a model for a two material system, why not use it? Okay, it gets more interesting though. He says, but because uniformitarians need to increase the time anyhow, they should not object to this approximation. So first of all, my question is, why do you need to increase time for a young Earth model of 6,000 years? Because remember, he's saying uniformitarians need to increase the time. But this is not the uniformitarian model. This is the young Earth model. So who needs to increase the time? Not the uniformitarians. It's the young Earth creationists. But then why do young Earth creationists need to increase time for a model that has only a model time of 6,000 years? So yes, I do object, because to me that makes things even more suspicious. And then to really top it off, he says the biotite would not be a significant hindrance to the helium flow in the uniformitarian model, and the results would not be too much different than those for a bare zircon. So he needs to increase time for the young Earth model, but then he goes back to a simple bare zircon model for the old Earth model. A very clear double standard. I will not comment more about that. You can draw your own conclusions. So let's now talk about the data. So this is what was published in 2003, and I'll walk through it in order. He had preliminary diffusion data. So this was known in 2003. And he knew by this time that biotite had a higher diffusivity than zircon. So had he created a bare zircon model, the red stars, just like he did for the RATE uniformitarian model, if you'd taken the RATE uniformitarian model, basically, and used it for the young Earth, I mean, basically you change the time, but you keep the boundary conditions the same. You would have these red stars. Not a very impressive fit. Now he makes this other statement. The extrapolation, this blue line, is from the measured data down to lower temperatures. And this is what Humphrey said. Later on, we will need a fit at temperatures below that. He says we will need a fit, and then he does the fit and publishes the coefficients, but he never refers back to it. He never refers to why he needs it. Okay? And then he shows the rate model. And what's interesting is he added this biotite shell. And by adding this biotite shell with the same diffusivity as zircon, even though his own data showed biotite has a much higher diffusivity, by adding that shell and making the diffusivity equal to that of zircon, he now gets 3 of his data points to lie very nicely on this extrapolation, which he said he later needed. Okay, this was all known in 2003. No predictions. There's no predictions at this point. This is all known data. So now come the 2004 results. Same graph. All I did was swap data sets. Gray squares are now just from a different experiment. Everything else is the same. And what's interesting is you can see that this good agreement between data, I'm just flipping back and forth, this good agreement really is just the fact that the measurement from 2004 lies along this extrapolation, which he calculated in 2003. And his model in 2003, which was tuned to lie upon this extrapolated line, yeah, that was already done. So it should be no surprise now that measurement and model agree. Because if you have this known, this is known, how hard is that of a prediction? Basically, the prediction is, if I run this experiment again, I'll get data points that fall along here. That's really all he's predicting. And lo and behold, you run a similar experiment, and you get data points that fall right along there. And to top it off, remember I said that he had unpublished data that was, in his words, ambiguous, and also of a lower diffusivity, because he said it had a larger effective radius, which if you do the math, that comes out lower diffusivity. So what he said is some of his unpublished data evidently came in somewhere in between here. Probably not as good of an agreement. So the low temperature data, remember, is very unreliable. It can change from sample to sample. If you look in the published literature, it changes. Even if the slope, the high energy part, high temperature part comes out very close, you see anomalies at the low temperature, because remember, Fenton and Koblitzer said this is where their model breaks down, and don't rely upon that data. So if you repeat the experiment enough, what are the chances of getting data to lie there? So to me, it's not remarkable at all. So I know I've gone long. I really appreciate your patience. I'll just finish with the statements. So Humphrey's last words were this. Rather than concoct fantastic theories and scenarios, I urge the critics to simply face to the most straightforward interpretation of the helium data, that the world really is as young as Scripture says it is. Okay, so my response is I've backed up every one of my claims with hard scientific evidence from multiple sources and rigorous modeling. Accelerated nuclear decay is a fantastic theory, not mine. And let me just elaborate on what Humphreys means by a straightforward interpretation. His straightforward interpretation of this helium retention of the zircons, his interpretation is that all rock stars and galaxies in the universe can't be much more than 6,000 years old because too much helium was found in zircon crystals from geothermal test wells in New Mexico. Too much helium, we can't account for it, therefore every rock, star, and galaxy in the universe must be about 6,000 years old. Problem, though, is that in 6,000 years, you wouldn't have any helium to begin with. Well, that's explained because in addition to that, nuclear decay rates were accelerated by a factor of around 500 million to account for the helium. But then if you have that, you would have so much heat, it would melt the Earth. But that was prevented because there was some cosmic cooling event that kept the Earth from melting from the intense radiation. So this is a straightforward interpretation. All rocks and stars must be 6,000 years old. Nuclear decay was accelerated, and thermal melting was prevented by a mysterious cosmic cooling event. In contrast, my fantastic theory and scenario is basically this, that in constructing a diffusion model, I could just take what's published in the literature. You can pick Reiners, Cherniak, Wolf, or Guntner. I can use the Harrison 1986 paper at face value, and that to interpret the geologic history requires really considering everything that happened from the Precambrian up to the Holocene and not just focusing on one volcanic event. And to him, that is fantastic. That's unrealistic. It's just wild speculation. So I think I should close here. Thank you, Steve. I know I went quite long and there's quite a bit of material. I hope you weren't overwhelmed by it.
That is quite all right. Well, it is overwhelming. That's kind of to be expected, but it's quite fine.
Good
That was
job, Gary.
definitely longer than we had expected. It's been 2 hours. I do, if you don't mind, just so we get it on this particular video, kind of go over just a couple of the slides and kind of break it down a little bit more simplistically. Maybe it'll take like 30 minutes at most. And I know we got to get Dr. Henke in here. I'm sure he has a lot to add. This is such a huge topic, but if we can go back to some of the slides and just kind of, for example, one of the things you had noted, can you go back to the slide that was talking about the Formula 3?
Yes, I'll go.
And then maybe Dr. Henke might want to like add something here.
Can you hear?
Yes, we can hear. Okay, so I was kind of taking mental notes, but this is such an in-depth topic. Now, on this particular thing that Humphreys is using for these formulas, now, again, correct me if I'm wrong, it looks something like he's using some kind of like Flick's second law of diffusion.
Mm-hmm.
But he's adding extra stuff to it. And your question to him is, so I want to make sure that if he watches it, your question is, how did he take something along the lines of an actual diffusion formula and expand it by adding that extra component to it, an extra term? Because I don't recognize that extra term. That first term in example 3, I've seen before. That's an actual diffusion formula, correct, for Flick's second law?
Right.
Okay, but the second one, I don't understand where that term comes from. And that's your question to him as well?
Yes, and why adding it is even appropriate.
Okay, because I want to make sure that that's out there, because I don't understand that either, why that extra term is in there.
And I think it's fair for him to either provide a reference or a proof. I'm fine with either.
Okay, fair enough. And one of these days we'll probably get somebody to actually have a hangout on this kind of math. This is Laplace transformations and partial differential equations and fun stuff. But obviously, I don't expect people on our live chat or people to watch this video are going to be just looking at it and not understanding. And I get that. But what the takeaway is from this particular slide is that the question is where did Humphreys get the derivation from this formula, and what was the reason for using it, basically, right?
Yes.
Okay, good. And the other things is if you want to go to the slide dealing with uniformitarianism, especially.
Which one?
Because I actually had found something, and if you go to
the one with the thermal history,
anyone that mentions uniformitarianism, I think this is kind of interesting. If you actually go to, I believe it's ICR. Let me see if I can find it again here.
Okay, so here, yeah,
he has a very different understanding of the word uniformitarianism. And he actually kind of states in the new rate data supporting young Earth, I think it's called the name of his blog. Let me see. New rates data support a young Earth or young world by Russell Humphreys. He actually says in here that uniformitarianisms assume that, quote, all things continue as if they were from the beginning of creation. 2 Peter 3:4, without interventions by God.
Can you hear me?
Yes.
Okay. Yeah, I'm having trouble with my microphone. I had some. Well, go ahead. I had some previous questions too. But
okay, one sec. Without intervention by God, which might dramatically affect the rates of some physical processes. Now, uniformitarianism, as you described it, and as I understand it, just makes the assumption that the processes, the geological processes and the laws of physics today are similar to the ones prior. There's some uniformitarianism there. Is it uniformity?
Yeah, actually, it's a lot simpler now. All they're saying is that the laws of chemistry and physics haven't changed over time.
And he's taking it to be completely different. He's taking it from a theological approach.
Well, yeah, he's quoting Second Peter, and if you look at Second Peter, it's talking. Well, actually, it's the words of non-Christian Jews, saying, ever since the time of the fathers, things have stayed the same. Well, if these were modern atheistic uniformitarians, they wouldn't refer to Moses and Abraham as their fathers because they consider them myths. If you look at the wording, it's a critique written by somebody, probably not Peter, in the 2nd century, attacking non-Christian Jews, and for basically saying things are staying the same. Where's Jesus? He's not showing up, because after several decades of Christians saying Jesus is coming soon, finally some of the non-Christians are saying, well, where is he? Things are the same now as they've been since Moses. And the young earth creationists take those verses out of context, out of historical context, and so forth. And I should also point out that even modern uniformitarianism, or I call it actualism, doesn't always say that the present is a key to the past, because you can look at certain rocks that formed in the past, like banded iron formations, that aren't forming today. All they say, modern uniformitarianism says, is that the laws of chemistry and physics have not changed over the past, well, since probably the Big Bang. And
So about 13 billion years, probably. Now there might be some changing. Correct me if I'm wrong, but there might be some initial conditions in the early formation of the universe during the Planck era, where that may not hold. And I think most people in physics understand that, right? So when they say it's continual and it hasn't changed much, we really mean from where it basically the universe cooled down and the universe started to form. There was actual matter, and ever since then, these things haven't really changed.
Right. We have the laws of gravity. If you react an acid and a base together, you're going to get a salt and water.
Right. And if I jump up, I'm going to fall to the ground, which, by the way, we tested just recently by Landon Kurt Knoll, as you know, who was down in South Pole, and he just tested gravity still works down there, believe it or not.
Yeah, that's all it's saying. Also, back in Formula 3, what Humphreys did was he developed the Arrhenius equation, which is the activation energy. The first, well, he split up his curves into intrinsic and extrinsic, and he developed, took the Arrhenius equation for the intrinsic and added it to the extrinsic, and then summed those up. That's why he adds those two together. And again, Gary's saying that's invalid.
No, run that by me again, though. I'm sorry.
Well, okay. You see the DO?
Yes.
Okay, that is, I think, for the intrinsic curve.
Correct.
And then the extrinsic curve, which is sloped differently, it has a separate. And then he adds them up to get a total diffusion. That's what he's trying to do back in his 2005 paper.
Yeah.
And
okay.
Gary's questioning that. So.
Yeah, and I just want him to either provide a reference or a derivation.
Well,
which I think it's quite fair to ask him for, and hopefully, if he does see this video, he'll be able to produce that.
Yeah. Also, I'd like him to explain Q0 and how present the notes to indicate that back in 1982, Gentry and others made a typo, so he can change his Q values. And there's again a whole list of things I covered last week.
Right, the Q and the Q sub naught, the helium retention. Right.
We have a long list of questions for him. I have my questions in Appendix C of my 2010 rate or Talk Origins essay. Gary has his questions, so he has a lot of work to do.
And I also want to address really quick, if we may, and then I probably should bring this to a close. The graph that Humphreys used, where he had a constant temperature. Can you kind of go into that in a little more detail? Because that's kind of difficult to understand why he took this understanding that he has of uniformitarianism and then make it such that he has a constant temperature with relationship to time here. I don't understand how he just got that horizontal line there.
Likewise, I mean, that is a question you really need to address to Humphreys. I've tried to give his defense of that as much as possible. I do see a tendency for him to oversimplify things, and quite honestly, to put together a varying temperature model takes more work. But it's one of those things. Once you do, it's very powerful, and even just looking at things from just a pure modeling point of view, his models tend to be very simplistic in the sense that built into the equations are assumptions, and then if you have to change anything, you have to look for new equations. I took a very different approach, and that is to create basically a general purpose partial differential equation solver. And if you look at what I did, I mean, not what I published, I mean the actual code, it's actually very interesting because I can just plug in a different thermal history. You give me a thermal history, I just plug it in. You want a different boundary condition, I just plug that in. And I use the same underlying solver for all of it. So there's an underlying consistency. So really, I can model a much wider range of possibilities than Humphreys can. And I don't know if this is just because he didn't know how to work with a more complex model. Was he just math limited? I don't know. I sometimes get that impression that when he faces, just like with the two material model from Bell, he goes to the literature, identifies the model, and then he says, we're not going to use it. He sort of sets things up saying, we will need this kind of model. He identifies it, but he doesn't use it because he says the math is complex.
Yeah.
And I'd say, well, yeah, if this is an important study, do it. I mean, just do it. I can understand if it's an average person, but you're a research scientist. If you found a better model, use it.
Yeah, if you're going to change the age of the universe down to 6,000 years, you better go through the math.
Yeah. Please do the math.
All the effects lined up in a row.
And show some rigor. So I don't know if this was because his view of history was this, or it was just an approximation he made because he didn't want to deal with a temperature changing over time. I don't know. But he tries to justify it by saying temperatures in the past were higher, which at least there'd be validity in that he'd have a lower bound to everything. He could say, well, at least what I have is a lower bound, and that would be true. But the problem is temperatures weren't higher in the past. They were lower just by every source until you get to some of these heating events mentioned by Harrison in the Precambrian. You can see the curves do cross past 800 million years. So you can say, yes, temperatures were higher in the past. In the deep Precambrian, when you had the crustal formation of North America and voluminous plutonic events, yes, it was higher back then. But from 800 million years on, there's plenty of time for these zircons to retain at least a good fraction of their helium.
Do you want to, like, before we wrap this up, take about a minute each just to kind of finalize this? Because this is obviously part 2. We're not going to have a part 3 on it. So if anybody has any questions on it, please leave comments in the video description below and email me or email any of these gentlemen. I'm sure they'll be happy to take your questions. But do you want to, like, sum it up in about maybe 1 minute each, and then we'll leave it at that? Because again, this is so much information. What you described in here is a little bit overwhelming, but it is amazing. The comments in the live chat, which I was responding to and trying to translate it into a more layperson's level, is just remarkable. People have been fascinated by this. They don't want this to end. Actually, they're actually really interested in this. Unfortunately, we've gone well over our time, so I do have to wrap it up. But if you want to take a minute each, why don't you, Dr. Loechelt, why don't you go first, and we'll have Dr. Henke go next. So just go ahead and take a minute, wrap it up.
Yeah, I think my final slide really says it the best. which view is a straightforward interpretation of the data and which one is a fantastic theory and a scenario? And I itemize it there. Is it the view that everything's 6,000 years old, that nuclear decay rates were accelerated, and that some mysterious cooling event happened? Or is it that you can put together a model and just use diffusivities published in the literature, thermal histories published in the literature, carefully take into account the entire geologic history from the Precambrian to the Holocene, put it in a model, and using conventional physics, match the data? Which one is straightforward? Which one is a fantastic theory? And that's my closing statement.
That's great. Dr. Henke, you want to give your closing as well?
Yeah, I really appreciate all the hard work that Gary's done here, and he's done an excellent job. People can certainly go to our publications online for more details, and maybe we can go into greater depth there.
Yeah, I would love to have you both back and maybe talk about some other subjects coming up here. You guys had both seen my presentation on polonium halos, which is another great subject and indirectly related to this. This is also related to Gentry's work. That's one area that I do know a little bit more about than the helium diffusion arguments. But if you wanted to come on and we can have it to talk about that and invite some other people in. I think the next time if I have you guys on about this, let's have like Steve on. He's a geologist person, and we'll have a few other people that I know that really enjoy this topic, and we could just talk about these things in more of an open format. Yes. So Steve Bowerman, he was in here last time, if you remember him.
Oh yes. I didn't know the last name. I just call him Steve the geologist.
Yeah, Steve the geologist, as well as a few other people. But I do have to end this because it is.
Well, I also just want to mention that I would encourage people to email me if they have questions at Kevin, Kevin, .r.henke, Henke, @gmail.com, because I don't usually monitor things on the web, but I certainly am happy to take emails and questions. And I just also mentioned that there's a lot of problems with Dr. Humphreys' claims, with his equations as well as the data that goes into them.
And we appreciate that.
Thank you very much, Steve,
and thank you guys. I can't express to you guys enough how amazing it is to have people of your caliber and your knowledge level come in and explain these things. And I do hope Dr. Humphreys takes this to heart. Again, this is not a slight against his religious beliefs or anything like that. This is the science, and they're going to promote young earth creationism as, quote, creation science. I firmly believe they should do so with the data. And I don't think the data is there. Matter of fact, I can actually say with some knowledge level that I don't see anything relating to what their claims being true. And I think that the presentations both you gentlemen have are more than enough data to show people that what they're claiming is just not the case. But I do want to give him a chance to respond. I think that's only fair. So when he does, I will take his emails and I will put them on the www.greatdebatecommunity.com webpage. It'll be under the forums, and that will be an exact copy of whatever he sends to me as far as his response. And to let people know that also on that page, www.greatdebatecommunity.com, we also have coming up attractions and shows that'll be on that page. It's under the coming soon page. So check that every so often, because we're gonna have a lot more topics like this with a lot of intelligent people like we have on right now. So Dr. Loechelt and Dr. Henke, I thank you guys very much for this. And we're gonna be doing this again, I think, probably pretty soon on like polonium halos or something, because I would really, really like that. Is that okay?
Sounds good.
Awesome.
Thank you very much for inviting us.
Thank you, gentlemen. Thank you, live chat, for listening, and we'll see you next time.